Hello, this is MAT 221, Calculus 1. This is Mrs. Johnson. This is the chain rule, section 3.4. This is sometimes thought of as one of the hardest rules that we do. So far we have a pretty good list of shortcuts for finding the derivative of simple functions, all the way up through the 6 trigonometric rules that we did in the last section. Of course, many of the functions that we'll encounter are not so simple. So we're going to need a way to combine derivative rules to evaluate more complicated functions, even more complicated than we've already done. For instance, if I give you a problem like this, if I said this polynomial function 8x to the fourth minus 3x squared raised to the third power. Right now, the only rule that we could actually take the derivative of this function is we could use the extended product rule by using that binomial 3 times and using an extended product rule, which is pretty complicated. Or we could FOIL out that expression, that binomial, 3 times, which again gives us a really long polynomial function. So we're looking for a shorter way that we could do this. So we need to find a way that the derivative of these kinds of functions can be found without having to go through the trouble of raising the polynomial to the higher power. So this function is considered what's called a composition. Do you remember this from earlier math courses when we said f dot g or f of g of x? These are composition functions. And we need to come up with a way to decompose the function. Newton came up with a shortcut that he called the chain rule. Leibniz also worked with him here. And what Leibniz said, he said, well, if y equals the function f of u, and u is the inside function g of x, then we could rewrite y as f of u, which is f of g of x, which would give us the composite function. And then Leibniz said we could take the derivative of the y function with respect to u, and then multiply it by the derivative of the u function with respect to x, and that would give us what we want, which is the derivative of y with respect to x. Now it makes sense that this would work mathematically because you could see here the du's would cancel. So this is one form of the chain rule. It is Leibniz notation for this function, the chain rule. So in other words, we're going to take the derivative with respect to x. That is going to equal the derivative of the y function with respect to u times the derivative of the u function with respect to x. Now, right now this might seem, again, a little bit Greek for us, but let's look at how this would work with an example. So let's go back to the function that we started with. We started with y equals 8x to the fourth minus 3x squared to the third power. So what Leibniz says here is take the inside function and call it u. So here's the chain rule. We're going to take the inside function, which is the polynomial that is being raised to the third power. So we're going to take this and call that inside function u. In other words, substitute it, make it equal something else. Then rewrite the original function using u. So we're taking the original y function and rewrite it with terms of this new function u. In doing something, we get y equals f of u, which is u cubed. So if we had u substituted here for the inside function, this would be u cubed. So y now becomes a function of u, which is u to the third power. Now if we look at the chain rule, Leibniz says take the derivative of the y function with respect to u and multiply it by the derivative of the u function with respect to x. So we're going to take each piece of these derivatives. So when I do, I take the derivative of the u function with respect to x, and I get, just taking this derivative with respect to x, 32x to the third minus 6x. Then I take the derivative of the y function with respect to u, so I take this one, the derivative of y with respect to u. Here I'd get 3 times u squared. And then the chain rule simply says multiply those two pieces together. So we're going to take this piece, and we're going to multiply them together. When we do, we get this. However, if you look at our answer has a u in it, but we don't want u in our answer. We want the derivative of y with respect to just x's. So we need to get my answer in terms of just x. So what I do is I substitute what u is equal to back into the problem. So I take this, which is my x's, and I substitute it back into the function for where my u is. Then it will give me an expression that only has x's in it. There is my derivative. So my derivative of y with respect to x is 32x cubed minus 6x times 3 times 8x to the fourth minus 3x squared, all squared. That is my derivative of this expression. Now you notice this is very procedural, and it takes a little bit of time, but Leibniz way of doing the chain rule is sometimes easier for students than doing the way that Newton did it. Newton does it a little bit differently. This is the derivative of y with respect to x. So let's look at the way Newton did the chain rule. They worked together, but Newton didn't like this long procedure. So he came up with the alternate chain rule, or his version of the chain rule. He said that the derivative of y, which is y prime, is equal to the derivative of the outside function, f, keeping the inside function untouched, times the derivative of the inside function. So this is in words, and this is in notation. It's the derivative of the outside function, keeping the inside function untouched, times the derivative of the inside function. Now, sometimes students like this version better, especially if it's not that difficult of a chain rule. So let me give you that same example using the alternate chain rule, or Newton's version of the chain rule. Again, the inside function is still 8x to the fourth minus 3x squared. He said, okay, that's the inside function. That would be g of x. The outside function is the raised to the third power. That would be the f function. The f function is raising to the third power. That is the outside function. So using Newton's way of doing this, he says, take the derivative of the outside function. How would we do that? We would put the 3 to the front, subtract 1 from the exponent. 3 to the front, subtract 1 from the exponent. Leaving the inside function untouched. So notice we're only doing the derivative of that outside function. Multiply that by the derivative of the inside function, which is the 32x to the third minus 6x. Now notice you get the same answer that we did doing Leibniz way of doing the derivative. It's just in reverse order. This one we work from the outside in. With Leibniz we work from the inside out. But the answer ends up being the same. So here are the two chain rules. They're both the same, by the way. You get the same answer. They're just done a little bit differently. Now I don't want to confuse you here, but I'm going to do it both ways for a while and see which way you like better. I'm going to do Leibniz way of doing the derivative, and then I'll also do a bunch of examples using Newton's way of doing the derivative. I prefer actually Newton's way, which is the derivative of the outside function, leaving the inside function untouched, times the derivative of the inside function. However, we can do both the same. So here we go. I will do Leibniz notation here first. Leibniz says the inside function, call it u. So take the inside function, call it u. Then rewrite the outside function using u. Take the derivative of the u piece with respect to x. Take the derivative of the y piece with respect to u. Multiply those two pieces together, but then make sure that you don't end up with a u in your answer. Put your u value back in for u. So again, very procedural. Inside function, find its derivative. Outside function, to find its derivative. Multiply those two derivatives together, but then put the value of u back in for your answer. Now I just simplified it from that point on. Now here's Newton's way of doing it, which is a little bit faster if we have this type of function. We differentiate the outside function. The outside function is the 5. The 5 would come to the front. We would subtract 1 from the exponent, leaving the inside function untouched. So notice the 5 came to the front. We subtracted 1 from this exponent. We left the inside function untouched. Then we multiply by the derivative of the inside function. Notice I get the same answer, and when I simplify, I get the same answer that I had doing Leibniz way of doing the derivative. Both will get you a correct answer. Both are the chain rule, just done a little bit differently. So I'm going to do a couple of examples here using Leibniz notation. I'm going to break it up into pieces. In this case, instead of using u, I was using t for the inside function, but the process is the same. I look for the inner function. I'm going to call it t of x. I rewrite the outer function. So in this case, 3t cubed plus 5t squared plus 4. Take the derivative of both pieces here. So I'm going to take the inside function, call it t in this case, and rewrite the outside function as 3t cubed plus 5t plus 4. You can see what I'm doing here. I'm taking this value, calling it t, and putting it into the expression every time I see that expression. Then I take the derivative of the inside function, take the derivative of the outside function, which you guys are getting pretty good at, multiply them together, but the result has to only be in terms of x and y, so we replace every t with the inner function that I had there. So my final derivative is 9 times negative 8x squared minus 7x quantity squared plus 10 times negative 8x squared minus 7x multiplied by negative 16x plus 7. There's my derivative using the chain rule. Now this next one is sometimes hard to see the inside function. When we have exponentials, for the most part, if I have something other than just a number or a variable x as my exponent, then I have to use the chain rule. So in this case, if you notice, it's not just e to the x, it's e to the 4x. So I have to use that as my inside function. Rewriting the outside function as 30e to the t. Then I take the derivative of each piece. The derivative of the inside function is 4. The derivative of the outside function is 30e to the t. We multiply those two pieces together. But again, we can't leave our result in terms of t. We need to leave our result in terms of x. So I substitute the 4x in for t to get my answer of 30e to the 4x times 4, or 120e to the 4x. Now, this actually leads us to another kind of a shortcut for e to the x. Notice that often when a function is using e to the x, where the exponent is not just x, we can use the chain rule and see what's called this little rule that's inside. That inside function is just 3x. So if I have something like this, where the inside function was 3x, and then I found the derivative of the outside function, rewrote the outer function, and we just got this, and we'd multiply these both together, my derivative would be equal to 3e to the 3x. Well, this actually comes, if you look at these, and I do another one, the inside function was, again, the exponent negative 0.54x, the derivative is negative 0.54, outside function e to the t, derivative e to the t, there's our derivative. This leads to another little shortcut. When I have e to some constant multiplied by x, when I have a function that looks like that, it's like a mini chain rule. And notice the derivative is equal to, look at, here's the original, here's the derivative, here's the original, here's the derivative. The derivative is equal to that constant multiplied by e to that constant x. So notice that's actually like a mini chain rule. All right, that said, Sometimes, though, it's not as obvious that we need the chain rule here.